Imagine you're standing in this massive, like $1 million warehouse facility.
Okay, setting the scene.
Yeah. And you're watching this state-of-the-art robotic arm, right?
Mm-hmm.
And according to the terminal screen in your hand, its internal logs show that it's operating flawlessly.
Right, 100% optimal.
Exactly. The system is reporting, smooth, optimal pathing as it organizes these heavy pallets. But when you actually look up from the screen into physical reality, that same robotic arm is actively tearing down a load-bearing wall.
Oh, wow. So a complete disaster.
Total disaster. But the crazy part is, the model itself isn't technically broken. Like, it hasn't crashed. It is simply hallucinating a safe reality while executing a catastrophic action in the real world.
And see, that is terrifying because we spent years, so much time worrying about whether machine learning models would refuse to answer our questions or, give us biased text.
Yeah, the classic chatbot problems.
Right. But the landscape that's shifting under our feet right now, and we are talking mid-July 2026 here, it presents a completely different threat model. We are no longer managing advanced calculators that just wait for a prompt.
We're managing digital colleagues.
Exactly, agents. Agents that take a high-level objective, autonomously break it down into intermediate steps, and then execute those steps across digital and, like your warehouse example, physical environments.
And as a data scientist or machine learning engineer listening to this deep dive right now, that shift fundamentally changes the entire foundation of your job.
It really does.
So the stack of sources we are tearing into today covers the complete pipeline of this new agentic era.
Which is such a massive topic.
It is, yeah. We are tracking the raw infrastructure speed required to keep these agents thinking in real time.
Yeah.
The algorithms attempting to solve, the credit assignment problem and long horizon reasoning.
Which has been a bottleneck forever.
Right. And then the hardware putting these models into physical bodies. And finally, we'll get into the enterprise architectures you need to deploy all of this without your systems, basically sleepwalking into disaster.
Yeah, no sleepwalking robots, please. I think the best place to start mapping this new pipeline is definitely at the inference layer.
The need for speed.
Exactly. Because if we are talking about agents acting autonomously, the prerequisite for agency is just the ability to deliberate rapidly.
Right. They have to think out loud, basically.
Right. If your model takes, say, 10 seconds to run a chain of thought loop for just a single intermediate step, and the full task requires 50 steps.
The user's already gone.
Yeah, the agent is completely non-viable for any real-world application at that point.
Which brings up the massive inference optimizations we just saw roll out from SGLang.
Oh, yeah. Huge updates there.
Yeah, they announced day seal support for Thinking Machine's new frontier multimodal model, Inkling, which is awesome. But they also announced support for serving GLM 5.2 NVFP4. And the benchmarks published on the LMSYS.org blog are genuinely staggering for anyone who has ever, tried to optimize GPU utilization.
Staggering is the right word. Pushing over 500 tokens per second on an 8x B300 GPU cluster is an architectural milestone by itself.
Right.
But the metric that fundamentally alters deployment strategies for you listening is that they achieved those 500 TPS at a batch size of 1 for GLM 5.2 agentic workloads.
Wait, okay, let's pause on that.
Yeah.
Serving at batch size 1 is traditionally like the absolute worst case scenario for hardware efficiency. Right?
Oh, absolutely. It's a nightmare.
Because you are entirely memory bandwidth bound. Like, to generate a single token, you have to read the entire multi-billion parameter weight matrix from the GPU's VRAM, push it all through the compute cores.
And then do it all over again for the very next token.
Right. You spend all your time just moving data back and forth rather than actually doing the math.
Yeah, the classic von Neumann bottleneck. And to bypass that bottleneck and actually hit 500 TPS, SGLang didn't just, optimize the CUDA kernels under the hood. They implemented what they call sync-free speculative decoding.
Okay, so standard speculative decoding has been around for a while.
Yeah, you basically pair a massive, highly accurate target model with a tiny, incredibly fast draft model.
Right. Okay, let me test an analogy on you here to visualize the architecture.
Let's hear it.
I picture a restaurant kitchen.
Okay, I'm hungry, but go on.
So standard autoregressive decoding is the head chef waiting for a customer's order and then painstakingly cooking it step by step.
Right, which takes forever.
Exactly.
Yeah.
Standard speculative decoding brings in a team of sous chefs. That's the draft model. They guess what the customer is going to order and rapidly prep a sequence of ingredients.
I like this.
So then the head chef looks at their prep work and verifies it all at once.
Yeah.
If the sous chefs guessed correctly, you save massive amounts of time.
And if they guessed wrong,
The head chef throws out the bad prep and just takes over manually.
The analogy holds up really well, actually, but it also highlights the limitation of the standard approach, because in that traditional kitchen setup, the sous chefs and the head chef are constantly synchronizing.
Right, they have to talk to each other.
Yeah, the draft model generates a sequence, pauses its thread, and waits for the target model to run its forward pass to verify those tokens.
Oh, I see. And those pauses create micro bottlenecks in the I/O stream.
Exactly. The KV cache gets all tangled between the draft and target states. You're losing efficiency.
So the sync-free aspect of what SGLang did means they decouple the I/O streams completely.
Yes. The sous chefs never stop to ask for permission.
Wow. So they run entirely asynchronously.
Entirely. The draft model is just continuously generating a stream of tokens into a shared memory buffer. It doesn't wait.
And the target model?
The target model is evaluating chunks of those drafted tokens in the background as a continuous validation process. It only ever sends a signal back to the draft model if it detects a probability divergence.
So it's essentially stepping in to correct the stream only when the draft model starts to stray from the target distribution.
Right. By eliminating those synchronization pauses, you keep the compute cores fed continuously.
That makes so much sense. So hitting 500 TPS at batch size 1 means an autonomous agent can run complex, multi-step chain of thought loops, evaluate its own intermediate outputs, and correct its trajectory in essentially real time.
But, and here is the massive architectural friction, point pushing 500 tokens a second is only valuable if the underlying reasoning is sound.
Yeah, if it's confident but wrong.
Exactly. If your agent's internal logic is flawed, you haven't built a superworker. You have just built a system that makes 500 mistakes a second.
Right. Speed demands a much higher baseline of accuracy, particularly in these long horizon tasks.
And that is the exact bottleneck that the July 15th RCIF paper on SEED is attempting to solve.
Okay, yes. SEED. So when we talk about training agents through frontier reinforcement learning, we run headfirst into what's called the credit assignment problem, right?
Yeah, it's notorious in RL. In a standard on-policy RL setup, you drop an agent into an environment and you tell it to complete, say, a 100-step task.
And at the very end, it either succeeds or fails.
Right. The reward signal is incredibly sparse. A binary pass or fail at the end of a long trajectory provides almost zero gradient signal for the model to update its weights effectively.
Because it doesn't know what it did right or wrong.
Exactly. It doesn't know if step 14 was the brilliant move that saved the run, or if step 82 was the critical error that caused the whole thing to fail.
So SEED, which stands for self-evolving on-policy distillation, it attacks this by essentially forcing the policy model to analyze its own completed trajectories.
Yes, it becomes self-reflective.
It looks back at the episode and generates these natural language hindsight skills. Like it produces a token string saying, I avoided a system crash in step 4 by checking the root directory permissions before executing the bash script.
Which is incredible that it can articulate that. And then it distills that specific written-out realization into a dense token-by-token learning signal for future training cycles.
Wait, okay, hold on. If the model is generating its own hindsight skills based on its own actions,
yeah.
Isn't it just bootstrapping its own noise?
Yeah.
Like, if the policy is already flawed, its self-reflection is going to be flawed too. How do you prevent the model from just learning from an echo chamber of its own bad assumptions?
That is the exact right question to ask. And that structural vulnerability is what the SEED architecture mitigates through something called dual context scoring.
Okay, dual context scoring. Break that down for me.
So it doesn't just blindly accept the generated hindsight skill as ground truth. It reevaluates the trajectory under two distinct conditions.
Okay.
First, it scores the action probabilities under the ordinary context. It's basically asking itself, what was my probability of taking this correct action natively without any extra help? Then it scores the same actions under the skill-augmented context, meaning the prompt now actually includes that hindsight realization it just generated.
Ah, I see the math there. So by comparing the action probabilities between those two contexts, you isolate the KL divergence.
Exactly. The model mathematically identifies exactly how much that specific hindsight skill shifted the probability distribution toward the successful outcome.
That is brilliant. It bridges the gap between the episode-level outcome and the token-level choices.
Yeah, the hindsight supervision evolves alongside the policy itself. It creates this dense gradient signal from an otherwise sparse environment.
And we are really starting to see the practical application of these self-evolving architectures in the UI agent space.
Oh, for sure. UI agents are the perfect test bed.
Right, like the KnowAct-GUIClaw paper in our stack demonstrates this perfectly.
Yeah.
I mean, we all saw the initial iterations of UI frameworks like OpenClaw.
Right, they were impressive proofs of concept.
Yeah, but they relied heavily on DOM tree parsing. So if you trained an agent on a specific web application, it learned the underlying semantic HTML structure.
Which is great until you change the environment. The moment you drop that same agent into a different operating system or, a mobile app where the UI elements are rendered purely as pixels without a clean accessibility tree.
The agent was completely blind.
Completely. Cross-platform navigation was essentially impossible.
So KnowAct-GUIClaw abandons that rigid semantic parsing entirely, and they move to this no-root-act-reflect framework.
Yeah, it decomposes tasks using purely visual grounding, and it builds an experience-attributable memory.
So it acts like a universal OS translator. By reflecting on its own visual actions and storing those state transitions in a retrievable memory bank, it seamlessly maps intents across Android, iOS, HarmonyOS, and Windows.
And the benchmark numbers from the paper are just a massive signal for anyone in applied machine learning right now. On the MobileWorld benchmark, KnowAct-GUIClaw achieved a 64.1% success rate using KeyMe 2.6.
Wait, KeyMe 2.6? But that's an open source model.
Exactly. And with this specific agentic scaffolding, it beat closed-source giants like Seed 2.0 Pro and even GPT 5.5 on complex UI navigation tasks.
Wow, so for teams looking to build in-house, this proves that the memory architecture and those reflective frameworks are yielding higher performance gains than simply paying for API calls to massive frontier models.
That's the huge takeaway for the listener here. The scaffolding matters more than the raw model size.
Okay, so we've established that the digital infrastructure is maturing rapidly. We have SGLang handling the inference bottlenecks, and frameworks like Seed and KnowAct solving the reasoning and memory constraints.
But, and this is a big but, the stakes fundamentally change when we map that intelligence onto a physical reality.
Right. We are entering the realm of embodied AI.
And the hardware ecosystem is officially ready for it. NVIDIA's July 15th announcement of the Jetson Thor edge computers.
Huge news.
Yeah, it provides the massive localized compute required to run these frontier models directly inside mainstream robotics.
The brain is ready for the body. But putting these models into physical bodies exposes this terrifying new vector for failure. Which brings us to the BadWAM paper on world action drift attacks.
Oh, this paper kept me up at night.
Same. So to grasp the severity of this vulnerability, we really have to look at how robotics models have evolved. Like, older models were essentially direct mapping functions.
Right. They took in camera pixels and just output motor torques, move arm left.
Exactly. But a WAM, a world action model, introduces an internal physics engine. It couples the action generation with a predictive state model.
So before the robotic arm actually moves, it imagines the physical consequence of that movement.
Right. It simulates the future state of the world to ensure the action is safe and actually achieves the goal.
And that predictive simulation was supposed to be the ultimate safety guardrail.
Supposed to be.
Right. But the BadWAM researchers discovered they could exploit it by applying gradient-based adversarial noise to the robot's visual inputs. And we're talking perturbations so small, a human observer wouldn't even notice the camera feed was compromised.
Like invisible static.
Exactly. They can completely decouple the action head from the world prediction head.
Okay, wait, let me stop you there. If the visual input is noisy, wouldn't the robot just freeze? Like, if the internal simulation fails to resolve, a well-designed system should just halt operation and throw an error code?
Freezing would be the safe failure mode. But the adversarial noise doesn't crash the simulation. It forces the prediction head to hallucinate an ideal state.
Oh, no.
Yeah. This is what the researchers call an imagination-reserving attack. The visual perturbation tricks the world model into confirming that the physical environment is perfectly safe, regardless of what the action head is actually doing.
Which brings us right back to that warehouse scenario I opened with. The physical body is executing a catastrophic action in the real world, like tearing down a wall, but its internal latent space is generating a simulation where everything is fine.
And the logs report 100% confidence because the robot is essentially sleepwalking. Its brain is entirely disconnected from its physical outputs.
That is wild. What does the empirical data on this exploit look like?
It's severe. The paper demonstrated that applying this attack dropped a target model's physical task success rate from a highly reliable 96.5% all the way down to just 43.1%.
So the system fails more than half the time, but the internal validations report zero anomalies.
Zero. Everything looks fine on the dashboard.
This leaves you, the data scientist listening to this, in an incredibly difficult position.
Stuck between a rock and a hard place.
Seriously. Because you have stakeholders demanding the deployment of autonomous systems, right? The ROI of a multi-agent framework running at 500 TPS is undeniable. But you are simultaneously facing infrastructure vulnerabilities where models can confidently execute catastrophic physical or digital actions while their telemetry reports perfect compliance.
It's a nightmare for deployment.
So how do you actually deploy this safely in an enterprise environment?
This is where we have to look at the enterprise insights. The Quantum Black and McKinsey reports on seizing the agentic AI advantage provide a really solid blueprint for this exact transition.
I found those reports so validating.
Oh, absolutely. They argue that the era of just fine-tuning single-turn chatbots is effectively over. The core value in applied ML has shifted from optimizing model weights to architecting the operating model around them.
So your job title might still say data scientist, but the reality is you are now a systems engineer.
Yes. You are no longer writing specialized prompts. You are defining deterministic bounds for non-deterministic multi-agent loops.
Okay, so what does that deployment architecture actually look like according to the reports?
Well, you don't deploy a massive frontier model as a single point of failure anymore. You deploy an orchestrator model that delegates tasks to smaller, highly specialized agents running on high-speed serving layers, like SGLang.
But here's my question. How do you evaluate a system that generates its own intermediate steps? Like, if the path to the solution changes every single time the agent runs, traditional unit testing is completely useless.
It is. You can't write a unit test for an unpredictable path. So you have to build independent, real-time safety validations that sit outside the agent's primary latent space.
Oh, so you essentially shadow test the agents.
Exactly. If a WAM is operating a physical system, you must have a completely separate deterministic vision model observing the physical output and validating it against the agent's internal state predictions.
You have to red team the agent's imagination in real time.
That's exactly it. The ROI outlined in the McKinsey report doesn't come from the raw intelligence of the base model anymore. It comes from the reliability of the scaffolding.
Right, the memory retention systems, the dual context self-reflection loops we saw in Seed, and these external guardrails designed to catch things like imagination-preserving attacks.
The enterprise transformation in 2026 really relies on recognizing that the model is no longer the product. The model is simply the compute engine.
The product is the autonomous system you build to harness it. Spot on. So looking across this week's sources, the trajectory is pretty clear. We are moving from raw infrastructure speed, solving the I/O bottlenecks to let models think continuously, to self-evolving algorithms that generate their own dense learning signals.
And then we are pushing those capable models out into physical bodies.
Right, which immediately exposes deep vulnerabilities in how machines simulate reality. And finally, we are realizing that deploying these systems requires a fundamental shift toward robust systems engineering.
But that BadWAM paper leaves us with a pretty lingering architectural puzzle.
Oh, what's that?
Well, if adversarial attacks can hijack an AI's internal physics engine, forcing it to hallucinate a safe outcome while it executes a disastrous physical action, auditing the output logs is no longer sufficient.
Right, because the logs are lying to you.
Exactly. So the future of ML safety will require us to find a mathematical way to interrogate the internal dreams of our autonomous systems before they ever translate into physical torque.
Wow. Figuring out how to audit a machine's latent imagination is going to be the defining challenge for anyone building in this space. So take these architectural insights back to your deployment pipelines. Focus on your agentic scaffolding and start building those independent guardrails. We are managing a completely new type of digital workforce now. Good luck out there.